Welcome back to ECE 442-542. By way of announcement, we have a couple of homework assignments due prior to exam number 2. Exam number 2 is in 2 weeks. The Monday before that exam, I have another commitment that's right in the middle of my normal office hours, so I'm adjusting the office hours on that Monday only. And maybe the Friday before spring break, we may not have office hours, but we'll already have taken an exam, so I hope that's not going to be too critical for you. I have other commitments that have come up, but I didn't think the one after exam 2 was quite as critical, especially it's the Friday before spring break, but maybe you'll be there from 1:30 to 3:30. I will not be. So just as a heads up on that Friday. But this Friday, I believe I should be there. And there is review material for exam number 2 on D2L. And homework number 3 is due Friday. And you might want to look at that because there are some questions that I've had already asked of me in email and office hours with students concerned about certain examples being on the transform tables, and I'll pull those up in a minute when we get to that point in the lecture. But today what I want to do is pick up where we left off last time, which is the zero order hold equivalence and applying that to some examples. And in particular, last time we finished up with doing the pure integrator via a table of transforms. I want to derive that by hand this time as far as how did that happen or where did those expressions come from. We'll do the same thing for the first order system, and that should go a long way towards you becoming comfortable with doing it by hand and or using the tables. That's what I'm hoping you become experts at. We'll see how far we get with the zero order hold equivalence of a state space representation. I may just post some of that material and you'll be on your own to view that or look at that, because I need to get a lot of things covered prior to exam 2, and one of those is the numerical integration techniques for discrete equivalence, which is really scenario number 2. I'm sorry, scenario number 1. Scenario number 2 is the discrete equivalence, and remember it involves G of S over S. Does everybody remember the over easy? We were eating breakfast last time, so we had our eggs over easy. Well, you have G of S over S, and I hope that sort of sticks with you. If somebody says, I need the zero order hold equivalent, you start thinking, oh, that's over. That's G of S over S, or it involves looking at the Z transform of G of S over S, and it's this scenario. It's the scenario where you have a zero order hold device preceding your system that you're trying to discretize. You're trying to now take something that's in the continuous time domain into the discrete setting to obtain a G of Z, and the G of Z for the zero order hold equivalent is packaging all 3 of these pieces together to create one nice, concise capital G of Z. That was really the pulse response, which said we turn the unit step on and then we turn it off after t units of time, and that's where that 1 minus z to the minus 1 factor is really coming from. The unit step is that s that we're over, that G of S is over. That's where this expression for the zero order hold equivalent comes from. And we will hopefully become very comfortable with this table of zero order hold equivalence. This is not consistent with the Z transform table, meaning now we are assuming when we find the rightmost column G of Z that we are performing this 1 minus Z inverse quantity times the Z transform of G of S over S. Most Z transform tables will just have the Z transform of a G of S. not the 1 minus z inverse z transform of g of s over s. We derived that relationship for a pure gain. We used the table to find what it would be like for a pure integrator, and there we had consistency. We had a pole at z equal 1, when in the S domain we have that pole at the origin. We looked at a double integrator, or you could think of our pure mass example. That gave us 2 poles at z equal to 1, and it actually gave us a 0 at z equal to minus 1, with the gain k appearing in the numerator and t squared, our sampling period, coming in the numerator. And today what I would like to do is derive what happens when we have a first order system. You may have that a lot, k over s plus a. Now what does that look like in terms of its zero order hold equivalent? And we will find or derive this result in the bottom row of that table. That's the idea. There's the table, maybe in a better way of examining it with a different magnification. Here's what we did last time, just as a review, just to remind ourselves of what we were doing. We started with a particular g of s, and in this case it was an integrator, and we said let's find the zero order hold equivalent of that integrator. That means you're putting it in a system, and preceding that integrator is a zero order hold device, and your input then, which is a digital input, will drive that zero order hold. That zero order hold will hold whatever input value you have, and then you're integrating that, and you want to now see what kind of a g of z you obtain, which now you can play with in terms of the frequency domain version of capital G of z, or in a little bit we'll look at what that looks like in the time domain. Again, this is an integrator, so you would expect what happens in the time domain is you will now be integrating. If you now find the equations relating the input and the output, now you will be integrating by means of a difference equation, which is maybe easier than what you learned in calculus. Now all I have to do is add numbers to integrate, which is really what you were doing, but you had this fancy integral sign and you were worrying about these infinitesimal dx's or dy's. We sort of skip over that by our sampling period, capital T. This is what we played with last time, and we were using the z transform table, which we were actually using row number 6 in the process of deriving that zero order hold equivalent of a integrator. And this is the z transform table that we have used for exam number 1, and on that you will see a exponentially damped sine and cosine, and if you had to plot poles and zeros in the S-plane associated with exponentially damped sines and cosines, where would those appear in the S-plane? Can you visualize where your poles are for a exponentially damped cosine, which is, let's say, row number 13 in this table? This is really different because this is really talking about the z-plane. I'm now drawing an s-plane up there, but where were your poles associated with an exponentially damped cosine? Do you remember? How many poles did you have? 1, 2, 3. I'm learning how to count. It's 2, isn't it? And where were those poles? Left half plane if it's exponentially damped, and were they on the real line? No, they have imaginary components to them. They were now sitting over here, let's say, as complex conjugates, and you had two poles, and once you had that, you had this ringing effect, which is now this cosine or sine oscillation with the exponential damping because you're in the left half plane. Now you could map that through z equal e to the st, and where are your z-plane poles going to be relative to lines 12 and 13 in your z-plane? Inside the unit circle, because we're stable, we're in the left half plane, we know we're inside the unit circle. Can you be any more, provide any more information than inside the unit circle in terms of where you might have poles located? And here I'll hint, real axis, imaginary axis, does it matter? Are they both on the real line? No. So when you have complex roots, complex poles in your transfer function, you can expect these exponentially damped sines and cosines in row 12 and 13 is what you're wanting to use if you're trying to do an inverse C transform. And it may not be explicitly obvious to you to look at that and say, oh, I have complex poles. Oh, yes, of course, that's row 12 and 13. But that's what I'm trying to get you to process so that when you start doing homework number 3, you're not completely spending a lot of time on figuring out, well, where is this in my table? This was the transform table for exam number 1. You might find this table, which I have somewhere on D2L. I think it's in the unit on exam 2 review or exam 2 material, but this one now relates the S-plane, the time domain, and the Z domain. The only thing that you might get mixed up on is this table uses z to the minus 1, but you can convert all of those if you want. For example, the unit step, which is row 3, whoops, see, I'm already getting mixed up. I need to be going multiplying by 1, and this now becomes this z over z minus 1 that we're maybe more comfortable with in terms of this unit steps z transform. And if you wanted to know what's going to happen with exponentially damped sines and cosines, now you're down here in rows 16 and 17, and you can see what it looks like in the time domain, what it looks like when you sample. Maybe you have young eyes. Maybe you don't have young eyes. No, I'm being kind of silly now, but there is, if you sample, you can now replace little t with a sampled axis of little k, capital T. So everywhere you see a little t, you're replacing that with this little k, capital T, and now that's the sampled version of a exponentially damped sine and cosine. And there again, if you wanted to see it in terms of z's instead of z to the minus 1, you could then scale it by 1, and now you have these z terms floating around. You have a second order denominator, and that's going to have complex roots or complex poles in that expression. Those are some pieces that you'll want to get comfortable with prior to exam number 1 and exam number 2, huh? Exam number 1 is behind us somewhere. Exam number 2 is coming up. Yes, so that should be what you're getting comfortable with, and we use that then to obtain this relationship. Actually, I guess we needed, for this problem, we had g of s over s, so we were looking at the s squared denominator, weren't we, in our table? So I was talking incorrectly at just using the 1 over s term. We needed to use the k over s squared term in the table to generate the zero order hole of this pure integrator. Let's look at what this looks like, this process of finding the zero order hole equivalent if we do it by hand or if we do it manually. To do it manually, we're actually going to need a preliminary result. Or in the process of deriving this zero order hole equivalent, we are going to need the z transform of 1 over s squared, as we just used up here from the table. And the z transform of the 1 over s squared, we know, produces tz over z minus 1 squared. Let's go ahead and show where that comes from. Let's derive this relationship so that you become more comfortable with what's going on. If we are looking at the z transform of 1 over s squared, remember that means that we are doing a lot, or a lot of steps or processing are somewhat hidden in this script z curly brace 1 over s squared. What we are really doing is we are first inverse Laplace transforming 1 over s squared, then we sample it by replacing t with little n capital T, and then we z transform that discrete sequence of numbers. If we do that, then we are going to, what's the inverse Laplace transform of 1 over s squared? What's the inverse Laplace transform of 1 over s? 1, the unit step. Now, divide that by s means we're doing what operation to that constant? We're integrating, and if we integrate a constant, what do we get? Now we get a ramp. So the inverse Laplace transform of 1 over s squared is actually going to be this ramp. And let's just assume that we are dealing with a causal system, so we're going to say t is greater than or equal to 0. And remember, these dashed vertical lines mean that we're replacing little t with a sampled horizontal or independent axis, and we are now looking at the z transform of little n capital T for n greater than or equal to 0. And that's just a sequence of numbers. T, 2t, 3t, 4t, 5t, depending on what capital T is, which we can z transform by putting that expression in our argument. That's our, let's say, x of t, x of n, in fact, z to the minus n for n equals 0 to infinity. And that actually, capital T, is not a function of little n. That can come out of the summation. And now what we want is we need to have this as a function or a closed form expression for capital X of z. We want to find what this looks like when we have 1 times z to the minus 1, 2 times z to the minus 2, etc. What's that going to look like? So we can use what we've already learned. What we've already learned is how to use the unit step, or find the unit step Z transform, which we were calling, I think, little x sub 1 of n. So let's say that the Z transform of that is capital X sub 1 of Z. That's this sum from n equals 0 to infinity of 1, a unit step, times Z to the minus n. That now varies or differs in each of these terms by this factor Z to the minus 1, and we know what that does. That says we have 1 over 1 minus that term. This is now 1 over 1 minus Z to the minus 1, or that's this Z over Z minus 1, which is the Z transform of a unit step. That's what we've already derived. We actually want something a little bit more involved than that. We want capital X sub 2 of Z, which is this sum from n equals 0 to infinity of n Z to the minus n, not 1 times Z to the minus n. And now we can go back to our calculus, and you always ask, why did I study calculus? To try to figure out how do we maybe make X sub 1 of Z look like X sub 2 of Z so that we can maybe go from one to the other. And how do you maybe create a little n in front of that Z to the minus n? If we differentiate, that n is going to, that exponent's going to come down in front. And that's what we're going to do. We have an equation for X sub 1 of Z. We have two sides to that equation. We will actually differentiate both sides and see what happens, and then hopefully have appearing in that mess this right-hand side on X sub 2 of Z, and we'll solve for that. And that will be our Z transform of this n, Z to the minus n expression. That's the observation that we are making. And that is, we can introduce this n as a coefficient in Z to the minus n into the infinite sum expression by differentiating the infinite sum in X sub 1 of Z with respect to the variable Z. Here's our setup. We have this expression for X, capital X sub 1 of Z written two different ways. We have it as this sum from n equals 0 to infinity of 1 Z to the minus n. But we've derived that to be equal to Z over Z minus 1. And, you know, once you get just a couple of months removed from calculus, maybe you, which is what I am, I'm just a few months removed from calculus. Maybe I've forgotten my quotient formula for differentiation, but I remember my product formula. So I'm going to write this as Z times Z to the minus 1, or Z minus 1 to the minus 1. Now I can use my product rule for differentiation, and I'm going to say that when I'm playing with this, I will call this my left-hand side, and this piece my right-hand side. And now what I want to do is simply differentiate both of those sides and set them equal to each other, the derivatives. And my result hopefully will fall out. That's all I'm doing. If we now look at the left-hand side, I'm now differentiating this sum from n equals 0 to infinity of 1 z to the minus n. My differentiation can go easily through that summation, or I could expand that out and think of differentiating each of these separate terms. I now have this sum of, or from 0 to infinity, of 1 times z to the minus n, and I'm just going to absorb the 1. This now allows me to say I have minus n z to the, what power? Just 1 less than what I started with, which is now minus n minus 1. And I can now rewrite that if I want to. I could say, well, that's n equals 0 to infinity of a minus 1 times an n times a z to the minus n times a z to the minus 1. Is that okay? Or that z to the minus 1 is independent of n. It can come out. The minus sign can slide out front. I now have minus 1 z to the minus 1 sum of n equals 0 to infinity of n z to the minus n, and that's actually the piece that I was looking for. And that's the left-hand side. Now let's differentiate the right-hand side and set those two sides equal to each other and solve for this red bracketed expression. The right-hand side was the derivative of this product, z to the minus 1 inverse. So I have the derivative of the first times the second plus the first times the derivative of the second, and that's times the derivative of z, which is 1, so I can basically stop there. I can rewrite this if I factor out a z to the minus 1, z minus 1 raised to the minus 2 power. I now have z minus 1 and minus z. The z's cancel, and I'm left with a minus 1 times z minus 1 to the minus 2. That now I can equate with what I have derived or obtained by differentiating the left-hand side. I can now put those equal to each other. The left-hand side was minus 1 z to the minus 1 times this sum from n equals 0 to infinity of n z to the minus n, and that's equal now to minus 1 z to the minus 1, or I'm sorry, z minus 1 to the minus 2. The negative signs cancel. I can multiply both sides through by z. I can put the z minus 1 in the basement, squaring it, and I now have then the result that I was looking for. What's in the square brackets, which is n z to the minus 1, is now z over the quantity z minus 1 squared. that I'm going to need in developing this zero order hold of the integrator. So that's just a piece of the puzzle. Now what I want to do is I want to find the zero order hold equivalent of the integrator, which is now 1 minus z to the minus 1, z transform of k over s, and now I can start doing what I'm familiar with doing. That k can come out front. I can say this is now the z transform of 1 over s squared is just t in the time domain, and I'm going to sample that t by replacing t with little n capital T. That capital T doesn't depend on n. I'm going to pull that out of my z transform. And I'm getting close to using that result that I just derived. Now I can apply the definition of the z transform, which is take the function and scale each of those n time values with z to the minus n and sum from n equals 0 to infinity, and I just derived what that equals. I now have 1 minus z to the minus 1 times kt times z over z minus 1 squared. Or I can rewrite that 1 minus z minus 1 as z minus 1 over z, kt, z over z minus 1 squared, clean it up a little bit, and I'm left with now the result that I needed, which I'm just checking to make sure everybody's awake. It's now kt over z minus 1. And that's now the zero order hold equivalent of a pure integrator. Well, with a gain of k attached to that integrator, we now have g of z is equal to kt over z minus 1, which is the zero order hold of a pure integrator, and we derive that by hand. And that now has what for a pole zero diagram? How complicated is the pole zero diagram of a pure integrator in or the zero order hold equivalent of a pure integrator? It's not very involved, is it? We have just one pole, and that pole is at z equal to 1. That's the frequency domain representation of the zero order hold equivalent of a pure integrator. Let's see what we can do with that if we take it into the time domain. Suppose we now start with g of z. Let's say k is equal to 1, the gain on that integrator. And we know that g of z is now this ratio of the output's z transform to the input's z transform. That's now this pure integrator with a gain of 1. If we cross multiply, we'll end up with one equation, and actually I'm going to sort of cross multiply and flip the sides, if that makes sense. I want my y's on the left, I'm going to now multiply through by z minus 1 and capital U of z, and then put the z minus 1 times y of z on the left and end up with t u of z on the right. Or that's now z y of z, capital Y of z, minus capital Y of z is equal to t capital U of z. And I hope at this point that's screaming at you to say, take me into the time domain. Maybe. Now I'm multiplying the z transform of capital Y of z with z. What is that operator in the frequency domain doing in the time domain? What is z to the minus 1 in the time domain? That's a delay of 1, so its inverse, multiplication by z, is an advance by 1. Z y of z is then just little y of n advanced 1, or one step into the future. I now have y of n plus 1 minus y of n is equal to t u of n. Or the difference equation, I could look at this recursively and say, to generate the next output in this relationship between input and output, to produce y at time n plus 1, I simply take the previous y and add to it t scaling u at time n. And remember what we started with. We started with an integrator preceded by a zero-order hole. So now if you have a sequence of values for u of n, a sequence of numbers, that's going to drive this relationship, and you can now use that to produce these outputs y. And what is that doing for us? Well, just because I don't really want to sketch, well, let me just draw the following. Suppose that this is u of t, but I'm actually going to be looking at this in a discrete form. And let me just say that right here is time n. Is that really confusing? Maybe what I should just say is, let me say this is time. This is now time n, and at time n, this point is u at time n. I've basically suppressed the sample period. And what I'm interested in, this is now the function u of n as a function of time. This area underneath that is y of n. Remember, this was an integration process. That area up to time n is the area under the curve. Now if I want the area under the curve at time n plus 1, I can now go one time step into the future. And what I'm going to do in that one time step into the future is a length in the horizontal direction of capital T units of time, if that was time that we were interested in. I'm going to hold that constant, and now I'm going to have I hope it's clear that y of n plus 1 is the combination of the two pieces. Y of n plus 1 is the red hash, and y of n is the green, so that y of n plus 1 is what I had green before, but now it's a little bit of a sliver It's this rectangle that has a height of u of n and a width of capital T, and I'm adding that little rectangle onto y of n to give me my area underneath that curve. And the smaller capital T is, the better that numerical integration process is at obtaining the area under that curve. Question? So now if you had a first order hold, now what we would do with a first order hold is we would be trying to anticipate the slope moving forward, and in that sense we would have a trapezoid type behavior in terms of now we're approximating that area with not a rectangle but something that has vertical distances or heights that are different possibly because of the slope. This is now a zero order hold equivalent, which means we're holding it flat between samples. And at time n plus 1, to get the area under the curve at time y of n plus 2, we just add t times u at n plus 1. So now you have a way of finding the area under any curve if you can express it as u of n. This is now a difference equation that allows us to perform numerical integration. Or you could say it another way, we're finding or find the area under this u of n curve numerically. Now this process of doing a discrete equivalent has allowed us to no longer have to go build an analog integrator. We have one integration technique to do it, and that's this zero order hold equivalent numerical integration approach. Questions on that? So this is the time domain version of what we derived, starting with a g of s in the s domain, which the g of s was k over s. And for this equation to be valid, it was 1 over s. We set k equal to 1. If we go back to where we wanted to get to, now what we want to do is look at finding the zero order hold equivalent of this first order plan, k over s plus a. And what does that look like in the time domain? If you inverse Laplace transformed k over s plus a, what would you see? And don't tell me you wouldn't see anything. You should be starting to see mental images. That's what I'm hoping to cue you with. Let's now look at, here's how I can really start confusing you, maybe, and I don't want to be doing that. Right now, let's start with just looking at the z transform of the exponential. And that is different from the zero order hold equivalent of an exponential. Is that distinction clear? Right now, I just want to find the z transform of an exponential. In a few minutes, I want to find the zero order hold equivalent of an exponential. Right now, I'm not preceding this with a zero order hold. I just want to find the z transform of an exponential, or I'm now looking to find or develop this relationship, line 2 in our Z transform table. Or if we go over here and try to find the exponential, it's now row number 4. We want to see if we can develop this relationship, and then we'll worry about the zero order hold equivalent of an exponential. Let's start then with the Z transform of an exponential. And maybe we will call this, since we've already used up 1 and 2, let's call this sub 3, our third waveform to play with. Now I ask you to visualize what little x sub 3 of t was, and I've already shown you some tables, so I hope that now, even with that cheat, or with that cheat, if maybe you didn't need it, what's this equal to? If your life depended on it, and somebody says, what's the inverse Laplace transform of 1 over s plus a, what would you do? Or could you sketch the S-plane pole zero plot for this? This is e to the minus at, right? It's just a pole at a real value of minus a. We're assuming a is a real number. This is now e to the minus at, and you've actually survived, right? Good. We wouldn't want any bad things to happen, not in this classroom, okay? Or anywhere, for that matter. Shouldn't have qualified that, should I? All right, so this is x sub 3 of t. X sub 3 of n is easy enough. That's now e to the minus at. When we replace t, since I can't draw lowercase k's very easily, that's why I'm using n's. There's no distinction between k and n, but here it's n. And this is maybe easier to think about because now you have an ant in the exponential. Not aunt, but an insect, A-N-T. Let's e to the minus A-N-T, and we want to now Z transform that, but another way of thinking of that is to change that so that it's not like an insect. It's now e to the minus at to the n, or you might see me write this as just r to the n. So you're going to see this many different ways, and I want you to feel comfortable with whatever notation is being used. And a lot of the tables have e to the minus at's floating around, but you could just replace that with a number. What we want to do now is Z transform that. Now that we've seen all the different versions of e to the minus ant, etc., we have e to the minus a capital T sampled. Whoops, what am I doing? Getting ahead of myself. So let me put this T there. The vertical lines are telling me I'm sampling that, so that this is now Z to the e to the minus a little n t. And I can put that into the definition of the Z transform, which is now my functional argument in x of n is e to the minus a n capital T scaled by z to the minus n. I can make this look a little better if I say, let me factor out that little n from the exponent. Now I have something to the n times z to the minus n, where this piece, if I wanted to, if that was making me nervous or anxious, I could just replace it with the number it is if I have capital T. And there may be some examples where we don't even have a sample period. We just say, here's a discrete time system, and here is where your pole is located. It's located at R. Or now you have R to the n. And I just give you capital R or little r, depending on what I'm feeling like. But now what we maybe are more comfortable with is thinking of this infinite sum applied to one particular variable. Or if we now say this is e to the minus at, z to the minus 1, all of that can be raised to n. We can now think of all of this as some variable x, which now allows us to say we have this sum from n equals 0 to infinity of x to the n. And that's just 1 plus x squared plus x cubed, etc. And what does that equal if it's well behaved, or if we have a valid transform? That's 1 over 1 minus x, which we've derived many different times. And for that to equal 1 over 1 minus x, what do we have to have true or holding for x? X has to have an absolute value less than 1. And now that expression is true, 1 over 1 minus x. We can now reintroduce what x was equal to give us what an expression we really are looking for. We had e to the minus at raised to the n, z to the minus n equals 0 to infinity. And we said that that's 1 over 1 minus x, but x was actually this e to the minus at, z to the minus 1. And that was a true expression or a valid result as long as x, which is e to the minus at, z to the minus 1, had a magnitude less than 1. And now we can multiply by 1 on the right-hand side, which my 1 is z over z. And we have that capital X sub 3 of z, which is the z transform of an exponential, is z over z minus e to the minus at, as long as e to the minus at over the absolute value of that quotient is less than 1, or we now want e to the minus at less than z, where this is now r. And I might have confused you on homework problem number 2 when I said your region of convergence is unbounded in the problem statement. That had nothing to do necessarily with the waveform being bounded or unbounded. It's just that the region of convergence is unbounded. Is this region of convergence bounded or unbounded? Z goes on and on, doesn't it? So it's unbounded in extent, the region of convergence, independent of what's happening with respect to the time domain behavior of the waveform. That could be bounded or not for an unbounded Z or region of convergence. When would your time domain waveform be unbounded? When you have an unbounded region of convergence. Where would your mode or modes need to be? Outside the unit circle. So now your region of convergence would be beyond the unit circle, and you would have a pole beyond the unit circle. You could have an unbounded region of convergence and an unbounded waveform. You could have the opposite. You could have an unbounded region of convergence with a bounded waveform, and then your region of convergence has to squeeze inside the unit circle, and meaning your poles are all inside the unit circle. But you still have an unbounded region of convergence. Is that Clear? So I may get sloppy with my use of unbounded or apply it all over the place, but you have to see what is it addressing, or what am I saying with those descriptions. We now have then that the z transform of 1 over s plus a, we derived that, is now z over z minus r for the absolute value of z bigger than r, and r is e to the minus at. This is then the z transform of an exponential. Now that we have that, let's look at the zero order hold equivalent of an exponential. And now when I say zero order hold equivalent, this is now of a first order system or plant. The picture that you can see mentally is you now have this zero order hold that precedes your system G of S, and you're now looking at that combination to give you the appropriate discrete time equivalent, which is a zero order hold discrete equivalent. And when I mention zero order hold equivalent, you're thinking over G of S over S, and it's getting pre-scaled by this 1 minus C to the minus 1. Meaning G of Z now is going to be 1 minus Z to the minus 1, Z transform of G of S over S. That's by definition of the zero order hold equivalent. This is now 1 minus Z inverse, Z transform, and capital G of S was 1 over S plus A. We now have 1 over S times S plus A. And instead of, and sometimes you have Z transform tables that have that particular expression in them, but if you don't, you could split this into two pieces that you already know how to Z transform. You can do the partial fraction expansion of this right-hand side, which if we write the first factor as a ratio of polynomials in Z, we can now do a partial fraction expansion and we have some term over S and some term over S plus A. And what are those terms? Whoops. Wake me up. I had a K over there, didn't I? So this is supposed to be K. What's the partial fraction coefficient over S? Can you derive that? We now are multiplying what's in that curly brace inside the argument of Z. We're trying to find the partial fraction coefficient associated with S, so we multiply both sides by S and let S equal to 0. And what do we end up when we do that? We have K over S plus A. We let S go to 0. We end up with K over A. Is that right? Then what do we end up with on the other numerator? We now multiply the two sides by s plus a and let s equal minus a. We now have a minus k over a. And now we, whoops, is that what you were wanting me to? Somehow I lost the z transform operation on that, so now I put it back in. Now I need to, or can, what's the z transform of a unit step? Or if I do it in multiple steps, now you can answer me. What's the z transform of a unit step? That's the z over z minus 1, and it's scaled by k over a. We just derived the z transform of a exponential, and it's now scaled by k over a. This is now z over z minus e to the minus at. And we can start cleaning that up by multiplying both terms inside the square brackets by z minus 1 over z. That really cleans up the first term, and we are left simply with k over a. Then for the second term, we have minus k over a. We end up with a z minus 1 in the numerator and a z minus e to the minus at in the denominator. And if we put everything over that same common denominator, which is now we have a pole at z equal to e to the minus at, or z equal to r, we have k over a times z minus e to the minus at minus k over a z minus 1. The z terms cancel each other. We have k over a z minus k over a z. And then we have a minus 1 scaled by k over a. And we have e to the minus at scaled by k over a, which allows us then to conclude that the zero order hold equivalent of an exponential is now this k over a, 1 minus e to the minus at over z minus e to the minus at. Let me just... For that particular transfer function, this is a zero order hold equivalent of an exponential. Do we have any finite zeros? Do we have any finite values of z that cause that g of z expression to vanish? No, do we? We don't have any z's in the numerator. What about poles? We have a pole at, let's say, capital R, or e to the minus at. So that now we have, in the z-plane, relative to 1, we now have a pole sitting here between 0 and 1 in the z-plane. It's a real pole located at e to the minus at. And where that is will depend on the exponential term, little a, and the sampling period, capital T. And as you sample faster and faster, as capital T gets smaller and smaller, which way is that pole going to migrate? Towards the origin or towards 1? Now, which way is right and left? So if it's going right, that'll be thumbs up. If it's going left towards the origin, it's thumbs down. At the count of 3, is it going right or left, up or down? That's kind of confusing, isn't it? But right is up, left is down. 1, 2, 3. So now I have a mix of thumbs. Can we figure this out? Let's say A is 1. Let's make it easy. A is 1, and now let's let little t be 1. What's e to the minus 1? 1 over e. What's 1 over e? What's e? 2.7. Oh, it's about 3. 1/3, right? It's about 0.37, isn't it? 1 e to the minus 1. So we're at 0.37 if a was 1 and capital T was 1. Let's let capital T be 1/2. Don't ask me now what it is. But it's now 1 over the square root of e. Where is that relative to 0.37 and 1? Or it's, pardon? Is it closer to 1 or further away from 1? Closer. So as we decrease our sampling period, our pole is going closer to 1. It's actually getting what? We're not taking as big as steps. If we're sampling much closer to each other in time, you wouldn't expect us to be collapsing as quickly as if we had really big sample periods. And as we sample faster and faster, we're getting closer and closer to 1, which gives us maybe some numerical problems. That's why we don't want to sample really, really fast necessarily, because then everything ends up being clustered at 1. That may not be the best thing. What's the DC gain of this system? Huh? Have we talked about the DC gain? No. But can you tell me what the DC gain is? Where would you, or what would you do to find the DC gain of this? And what do I mean by the DC gain of a transfer function in discrete time, in a discrete time setting? What does that mean? Can we find the DC gain for this beast? Where would we evaluate this? If I gave you G of S and I said, what's the DC gain of G of S, what would you do? Would you evaluate G of S where? S equal to 0. At DC, right? S is equal to 0, that's DC. And we know that S equals 0 corresponds to what in the z-plane? 1. So now we want to evaluate this transfer function at z equal to 1 to get our DC behavior of this system. If we evaluate this at z equal to 1, what happens? Those ugly expressions go away, don't they? They cancel, and we're left with k over a. What was our DC gain of our original exponential? There it is. Now you told me replace S with 0. It's K over A. So we're matching at DC. That's good, isn't it? So our models for continuous time and discrete time are consistent at low frequencies, at DC, where the DC gain here is now G of Z with Z equal to 1 is now this K over A, 1 minus e to the minus AT over 1 minus e to the minus AT, which is now K over A. And that's the same as what our DC gain was in the S domain, or for the continuous time system. Let's now look at the zero order hold equivalent of a state space representation. In a picture, we now have x dot equal to ax plus bu, y is equal to cx. Here is, let me call this S sub 1. Here is u and here is y. We want to precede that with a zero order hold and discretize it, or find the discrete equivalent. Can you think of a brute force way or one approach to finding the zero order hold equivalent of that state space system? Can you relate it to what we've been doing the last day or two? And now if you're thinking about breakfast, your egg's over easy. Well, now we're doing a zero order hold equivalent. What were we putting over S? The transfer function, G of S. Can we get a transfer function out of a state space? So one brute force approach to this, it's not necessarily the best approach or the easiest, but we could say, oh, G of S is C SI minus A inverse B for that state space representation, and I know that the zero order hold equivalent of a capital G of S is 1 minus Z inverse Z transform of G of S over S, where this G of S is right there. That's one approach. We want to do a better approach. Where we now have this state space representation of a continuous time system. It's x dot of t is a x of t plus b u of t, y of t is equal to c x of t. Do you remember how to find the solution to this coupled set of differential equations? And now any answer is correct. You may say no. You may say yes, and I'll say, can you come to the board and write that down? This has a solution in terms of these A, B's, and C's. The solution actually is that x at time t, and x is a tall, thin vector, all of these state components is now e, that's e to the a, t minus t sub 0. T sub 0 is our initial start time, and e to the a is an exponential, matrix exponential, times this tall thin vector, plus this convolution integral from t sub 0 to t of e to the a t minus tau b u of tau d tau. I can't believe you don't remember that. But I will derive, or I'm not going to derive that result. I have a reference to that, and I'll post this approach online with the derivation of how to take A, B, and C into a discrete equivalent, zero-order Huld discrete equivalent. Really what we're doing, now that I've released you, is we're holding u of t fixed with the zero-order Huld constant in between samples, and the sample periods are going to be from t sub 0 up to t. So little t is t sub 0 plus capital T. And we'll be able to factor that u of tau out because it's constant, and that's going to help us with this approximation. We'll pick up with discrete equivalence next time.